let's continue on to the second page of fall exam review worksheet 1. This is on the second page here. Let's pick up with intermediate value theorem. And so the theorem says that if a function is continuous on the closed interval from a to b, then it passes through every y value between f of a and f of b. So we don't want to overthink this. All this is saying is that if as long as we have endpoints that are defined and the graph is connected between those endpoints, then whatever the y values are at those endpoints, we know that the graph is going to hit every y value between the y value that's specified at point A and the y value specified at point B. So let's say at point A the y value is 2 and at point B the y value is 1. Then we're guaranteed that every point for every value between 1 and 2 will have to exist somewhere on this graph, between the x values a and b, right? And that's just going to make sense just by looking at the graph, right? So for number 4, suppose that our function is continuous, defined for all real numbers x, for f of negative 5 equals 3 and f of negative 1 is equal to negative 2. So we know that the graph is connected, we have endpoints that are defined. So if f of x equals 0 for one and only one value of x, then which of the following could be true? Could be x. So f of x equals 0, so that's just crossing the x-axis. So it helps to just sketch the graph and visually convince yourself what the answer is going to be. So f of negative 5 is 3, I plot that point. F of negative 1 is negative 2. I know that the function is continuous between these two endpoints. So if I want the graph to cross the x-axis between negative 5 and negative 1, then the only reasonable value that is provided is going to be negative 2. Because negative 7, it's outside the interval, 0 is outside the interval, 1 is outside the interval, and so is 2. So only negative 2 will make sense. Okay. Extreme value theorem. All this saying is that if a function is continuous over a closed interval, then a function has a maximum and a minimum value over that interval. So when you see the word value, this is talking about y value. Okay. If I want to, so as long as the function is continuous and the endpoints are defined, then I'm guaranteed to have a highest, at least one highest point and one lowest point. It's possible that you may have more than one that is shared, but you're guaranteed to have the highest point and the lowest point somewhere between, somewhere on that closed interval. So for instance, maybe a graph that looks like this, right? Then you would want to, here there's only going to be 4 potential points that could be an absolute max and absolute min, either A, B, C, or D. So we always want to test the endpoints. We always want to plug the endpoints back into the original function to check the y values, and then we will also want to find the critical points, okay, by setting the derivative equal to 0, finding those x values and plugging all of them into the original function, and then checking to see what's the highest y value we see and what's the lowest. Okay, and we want to be able to do this, especially if we don't have the ability to look at the graph. Okay, and also to be able to show it algebraically. So let's look at number 5. Locate the values. Okay, again, the problem doesn't specify y values, but you're just going to have to infer that this is talking about y values. Okay, this occurs on AP exams as well. Locate the values where the function attains an absolute max and values where the function attains an absolute min. Again, these are talking about y values that they exist on a given interval. So we have our function. We want to identify our critical points and our endpoints and plug them all back into the original function. So we have our endpoints. Okay, so to find critical points, we can set the derivative, find the derivative. So x cubed becomes 3x squared, 3x becomes 3, and we set that equal to 0. Factor out the 3, x squared minus 1, so x equals 1 and negative 1. So we have our critical points, and we have our endpoints. Oh, another thing that I forgot to mention is that, well, we know this is a polynomial function, so we know it's going to be continuous. There's not going to be any breaks in the graph. If there were a break in this function between -3 and 3, then extreme value theorem is going to fail because it doesn't pass the condition of continuity. Right, so back to our critical points and endpoints. So we have 4 points that we need to test. So we plug each of these values back into the original function. So -3 in for x, and I'm going to get plug -3 in for x, I'm going to get -17. Plug 3 in for x, calculate that, that's going to get you 19. Plug in 1 in for x, you're going to get 1. Plug in -1 in for x, you're going to get +3. So now we just compare all the y values. Right? Obviously, the lowest y value you see is -17, and the highest y value that you see is going to be 19. So this is what they're asking for. When they're asking for absolute max and absolute min, they're asking for 19 and -17, not for 3 and -3. Even though those are the x values where the max and min occur. So that's something that you want to be very careful about. So we're going to choose B and not A. Okay? The absolute min value, this is asking for y values. Okay. Let's look at number 6. So mean value theorem. The function f of x is equal to x equals x to the 2/3 on closed interval from -8 to 8 does not satisfy condition of mean value theorem because, so mean value theorem has 2 conditions. Our function has to be continuous on the closed interval, and our function is differentiable on the open interval. So we know that the function is not going to have any breaks, so it's going to pass the first condition. However, if we want to determine whether the function is differentiable or not, we need to find the derivative and look to see are there any points that will make the derivative undefined. So we find the derivative, bring down the 2/3, subtract 1 from the exponent, so 2/3 x to the 1/3. And we see that we do have an x value that will make the denominator undefined, and that's going to be x equals 0. So therefore, it'll be part E. F prime of 0 does not exist. And we see that the point where the function is not differentiable is also going to it's going to fall between our endpoints. So it's going to cause the function to be not differentiable somewhere between our open interval, -8 and 8. Okay, number 7. If f of a equals f of b equals 0, and our function is continuous on the closed interval AB, then, so this looks a lot like Rolle's theorem, okay, except Rolle's theorem has a third condition that this is leaving out. Function needs to be continuous, function needs to be differentiable on the open interval, and the endpoints have to have the same y value. So this only fulfills 2 out of the 3 conditions for Rolle's theorem, so that means that Rolle's theorem is not going to apply. Okay, we have to kind of figure out where that's going to fall. Okay. So we know that condition function is not differentiable, is not specified, Rolle's theorem does not apply. So if a function is not differentiable but continuous and the endpoints being the same y value, then we could think of an instance where a graph like this occurs. Okay, so a graph like this occurs. So this graph fulfills both conditions. F of a is f of a and f of b. Oh, actually, here I have the graph being y values of 1, but should be down here at the x-intercept. But either way, we see that the function is continuous, but obviously not differentiable because there's a sharp point. So f prime of x may be different from 0 for all values of x on AB, and that's possible here. Right? There's no slope of 0, so therefore condition B will be the correct solution. Okay, for number 8, for what value of c between 0 and 1 is the tangent to the graph of f of x parallel to the secant line on the interval between 0 and 1. So this is basically highlighting the condition for mean value theorem. Okay. So tangent to the graph of f of x, this is the derivative function. Secant to the line on the interval between 0 and 1, this is talking about the slope at between the endpoints. So that's f of b minus f of a over b minus a. Okay. So we basically need to set up the condition for mean value theorem and solve for c. So we find the derivative. So e to the x stays e to the x squared becomes 2x. We also need to find the slope between the endpoints. So find the y values at endpoints. Plug 0 in for x, we get 1. Plug 1 in for x, and we get e minus 1. Okay. We set, we find the slope between endpoints. F of 1 minus f of 0 over 1 minus 0, that's going to get us e minus 2. And finally, we're going to set our derivative equal to our average slope, or our slope between the endpoints. So we can, we're not able to solve by hand. So we're going to use our calculator to either you can find the intersection between the two graphs by putting this both into your y equals in your graphing calculator, or we can just set everything equal to 0 and then just look for the x-intercept. So that's what I'm going to do here. Okay. And so if we look at the graph, okay, plot that, put that in, and if I try to do zoom standard, okay, let's see here. So if you try to zoom 6, you see that between 0 and 1, it looks like it crosses the x-axis between 0 and 1, but you may have to zoom in. But it's between 0 and 1, so I'm going to just zoom in and just change all the window, just to zoom in on the window to be between -2 and 2. Okay, and we see that the graph definitely crosses the x-axis between 0 and 1, and then we just need to find that x value. So you can just do second trace, look for 0, choose a left bound that is on one side of the x-axis, and choose a right bound on the other side of the x-axis, and we see that the x-intercept will be 0.351. So that's our solution there.